This video is going to define and discuss continuity. So casually, I can say that a function is continuous if you can draw it without lifting your pencil at all, if it doesn't have any holes or gaps or breaks in it. More formally, we say that a function is continuous at a point if and only if the limit as x goes to a of f of x equals f of a. So this is saying if the limit of the function value is equal to the function value. This means that three things must occur for continuity. First, the function must be defined. The function must exist. So that means if you look at my graph and you look at x equal 2, there's a hole in the graph there. So that means the function is not defined, and this function is not continuous at x equal 2. So the function has to be defined for it to be continuous. Second thing that has to happen is the limit as x goes to a of f of x has to exist. And if you take a look at my graph to the right at x equal 1, there is a jump in the graph. That means the left limit and the right limit are not the same. So our two-sided limit as x goes to 1 does not exist. And that's what this second statement is saying. If the function has a jump in it, that would be one reason why that limit doesn't exist, and that means it is not continuous, in this case at x equal 1. And then finally, the limit has to equal the function value. So when you find that limit, it has to equal the function value, and that is our definition of continuity. I'm going to give you a little bit more vocabulary here. We say that x equal 2 in my example, where I have that hole in the graph, that is called a removable discontinuity. A hole in the graph is always a removable discontinuity. It's a place where the limit exists, but either the function doesn't exist or the function value is not equal to that limit. And again, visually, that would be a hole in the graph. At x equal 1, we would call this a jump discontinuity because there's a break or a jump in the graph at x equal 1. And then finally, there is a third type of discontinuity that didn't appear in my example. We can have what we call an infinite discontinuity, and that occurs if we have a vertical asymptote on the graph. That would be considered an infinite discontinuity. All right, so let's take a look at some examples. What kinds of functions are continuous? I have a big list of functions that are all continuous on their domains. Polynomials, rational functions, radicals, trig functions, exponentials, and logarithms. So if you want to figure out where one of these 6 types of functions is continuous, you really just need to find their domain. All of these functions are continuous on their domains. So let's actually start with something that is a piecewise defined function. So I've got the function f of x equals x plus 1 when x is less than or equal to 1. F of x is 2 when x is between 1 and 2, including the 2. And f of x is 1 divided by x minus 3 if x is bigger than 2. Let's see if we can figure out if f is continuous at x equal 1, x equal 2, and x equal 3. So we'll start with x equal 1. And going back to our definition, there's 3 things I have to check. I have to check, does the function exist at x equal 1? So if x is 1, if x equals 1, I would plug 1 into that top definition. I get 1 plus 1 is 2. So my function exists at x equal 1. Then I have to figure out, well, what is the limit as x goes to 1? And since this is a piecewise defined function, I'm going to find my left and right limits separately. So if I'm on the left side of 1, I'm smaller than 1. So limit as x goes to 1 from the left, we're going to plug into that x plus 1, and I get 1 plus 1 is 2. Then to find my right limit, x is just a little bit bigger than 1. So now I'm going to look at that middle definition. So limit as x goes to 1 from the right of f of x is equal to 2. Because my left and right limits are both equal to 2, that means my two-sided limit is also equal to 2. So the limit as x goes to 1 of f of x does exist. It is equal to 2. And because that limit is equal to my function value, that means this function is continuous at x equal 1. All right, what about at x equal 2? Let's see what's happening at that location. So at x equal 2, I'm first going to figure out, does the function exist? So f of 2, when x equals 2, I use my middle definition. I plug in, well, there's nothing to plug in. I just get 2. So f of 2 is 2. Then I'm going to find my limits. My left limit means x is a little bit smaller than 2. If x is smaller than 2, we use the middle definition, and I just get 2. So my left limit is 2. For my right limit, as x goes to 2 from the right, we're a little bit bigger than 2. So now I use that third definition. I plug the 2 in. 1 divided by 2 minus 3 is negative 1. In this case, because my left and my right limits are different, there's a jump in the graph, and that means the limit as x goes to 2 of f of x does not exist. Because this limit doesn't exist, I can say that this function is not continuous at x equal 2. And in fact, this would be a jump discontinuity because my left and right limits have different values. Finally, let's see what's happening at x equal 3. So I'm going to start by plugging 3 in. If x is 3, that's bigger than 2, so we use the bottom definition. 1 divided by 3 minus 3, well, that's 1 divided by 0, and that's undefined. We can't divide by 0. And so as soon as I realize that my function is undefined at x equal 3, I can stop and say, no, this function is not continuous at x equal 3. And what's happening here, if you were to find your limit as x goes to 3, you're getting this non-zero number, this 1 divided by 0. That's going to go to infinity, and we're going to get an infinite discontinuity, or a vertical asymptote. All right, let's look at some more examples. Let's see if we can find any x values where the function is not continuous and identify the type of discontinuity. So we'll start with the function f of x equals 3x squared minus x. This is a polynomial. That was on my list of functions that are continuous on their domains. Polynomials have domains that are all real numbers. Polynomials don't have any holes or jumps or gaps or asymptotes. So that tells me that this function is continuous everywhere. It's continuous on its domain, which is all real numbers, and it has no discontinuities. So polynomials are continuous everywhere, don't have any discontinuities. All right, what about f of x equals secant of x divided by 2? This is a trig function, so it should be continuous on its domain. To find its domain, I'm going to think of secant of x over 2 as the reciprocal of cosine of x over 2. So 1 over cosine of x over 2. To find the domain, I know that anytime I have a fraction or division, the denominator can't equal 0. We can't divide by 0. So that means cosine of x over 2 cannot equal 0. I'm going to think about my unit circle. And on the unit circle, let's see, cosine is my x-coordinates. X is 0 when we have an angle of pi over 2, 3 pi over 2, or anything that's coterminal with those angles. So we can say that to find the domain, this x over 2, the angle x over 2, cannot equal pi over 2, that's my 90-degree angle, plus any multiple of pi. That's what this k pi means. K would be an integer. So pi over 2 plus any multiple of pi gives me a place where cosine is equal to 0, and so that's not going to be in the domain. I guess, though, this is still in the form x divided by 2 cannot equal pi over 2 plus k pi. So I should solve for x. I'm going to do that by just multiplying everything by 2. So x cannot equal pi plus 2k pi. Those are all the locations where the denominator is equal to 0. Those are all the points that are not in the domain of this function. So where is this function not continuous? It is discontinuous at pi plus 2k pi. So again, those are values where the function is undefined, where you get 0 in the denominator. Now, what kind of discontinuities are these? Well, you have this non-zero number 1, and when you plug in your pi or anything that's coterminal with pi, you're getting 0 in the denominator. This is going to go to infinity, or perhaps you remember that the secant function has vertical asymptotes. Because these are vertical asymptotes, these are infinite discontinuities. All right, let's do one more. Let's consider the function f of x equals x plus 3 divided by x squared minus 9. I'm going to start by just factoring out the denominator. This function is the same as x plus 3 divided by x plus 3, x minus 3. That x squared minus 9 is my difference of perfect squares. So this is a rational function. This function will be continuous on its domain. To find its domain, I know that the denominator can't equal 0. Division by 0 is undefined. So that means x cannot equal negative 3 or positive 3. So I have two discontinuities. The function is not continuous at negative 3 and at positive 3. X equal negative 3 would be a removable discontinuity, and the reason is because there's a common factor of x plus 3. Anytime your 0 of the denominator comes from a common factor, it is going to be a hole in the graph or a removable discontinuity. But we can also see this by computing. If we want to find the limit as x goes to negative 3, we would cancel those x plus 3's out, and then I would get 1 over x minus 3. If I plug in my negative 3, that's 1 over negative 6. I can see that the limit actually exists even though the function doesn't exist. So there's a hole in the graph there, and that is a removable discontinuity. Let's see, at x equal positive 3, x equal positive 3 is actually an infinite discontinuity. That's because there's a vertical asymptote at x equal 3. Or you can see if you plug x equal 3 into this function, you get 6 divided by 0. And so that means this is going to go to either positive or negative infinity. That would be a vertical asymptote. So x equal 3 would be an infinite discontinuity. All right, here's another example that's a little bit different. Let's see if we can find the constant k so that f will be continuous for all values of x. And I have the piecewise defined function f of x equals kx plus 2 if x is less than 1, and equals x squared if x is bigger than or equal to 1. So for this function to be continuous, the right and the left limits have to be the same. So when I approach x equal 1, from the right and from the left, I have to get the same number. And so if we're approaching x equal 1 from the right, we are bigger than 1. So I look at the x squared. I'm going to plug 1 in. I get 1 squared, or 1. If I approach x equal 1 from the left, I'm smaller than 1. So I'm going to look at that top definition, kx plus 2. I'll plug 1 in, and I get k times 1 plus 2. For this function to be continuous, these two expressions, these two limits have to be equal. So that means 1 has to equal k plus 2. And then I can solve for k, and I get k equals negative 1. So k has to be equal negative 1. And I didn't mention this, but really the only reason I have to really check at x equal 1 is where I have the potential for a break in this graph, this piecewise defined function. At other values of x, you're either on a parabola or a line, and those are continuous functions. It's just where that break is, we have to check and see, really do the two pieces of this graph line up. All right, I have one more topic to discuss in this video. One consequence of continuous functions is they will satisfy something known as the intermediate value theorem. So I have the intermediate value theorem written out on the screen. It says if f is continuous, So if we have a continuous function, that's what I have drawn in yellow, on a closed interval AB, such that f of a does not equal f of b. So I have two endpoints, and the y values of my two endpoints are different. And if k, y equals k, is any number between f of a and f of b, then there has to be at least one place where the function takes on that y value. So this is basically saying if you know that your function has a y value, let's say of 1, and another y value at 10, if that function is continuous, it has to take on every single value between 1 and 10. It has to take on every single number between those two outputs. And so here's an example of a problem that we can solve using the intermediate value theorem. We have a continuous function, and we know it has the following values described in my table. My first question says f has at least blank zeros between x equals 0 and x equals 4. So we are guaranteed to have a place where f of x equals 0 anytime we go from a y value that's positive to negative or negative to positive. So looking at my table, when x is 1, y is 2. When x is 2, y is negative 2. So somewhere between x equals 1 and 2, there has to be a place where y equals 0. And I can use the same reasoning from negative 2 to 7. Between those two y values, there has to be a place where the function is 0. And again, from 7 to negative 3, we have to have another place where the function is 0. So there have to be at least 3 zeros. Now there could be more, but the intermediate value theorem guarantees me that there will be 3. Part B says f of x equals 5 at least blank times. So now I'm going to do the same thing, but I'm going to try to think about where is the function smaller than 5 and where is it bigger than 5. So from negative 2 to 7, smaller than 5, bigger than 5, there has to be a place where the function is equal to 5. And then again from 7 to negative 3, there has to be a place where the function is equal to 5. So it has to happen at least 2 times. Finally, my last question, is it possible for f of x to equal negative 6 somewhere between 0 and 4? And so looking at these outputs, I actually see they're all bigger than negative 6. I don't see any numbers that are smaller than negative 6. But the question is just asking me, is it possible? And the answer is, well, yes, it's possible, but it's not guaranteed by the intermediate value theorem. I would have to have a number that's smaller than negative 6 to guarantee that I'll have a y value of negative 6. But again, the intermediate value theorem doesn't tell you what your y values are. You could definitely have a y value of negative 6. It could be anywhere. For example, it could drop all the way down to negative 6 from this y equal 4 and then back up to y equal 2. So it is definitely possible to take on really any y value without having more information. All right, that was my last example. I know there are a lot of different ideas in this video, so as always, let me know if you have any questions.